So today we are considering a specific type of sensor, just to basically as an example, just to understand what is the typical the typical mechanism by which a sensor operates. And we are in particular focusing on one of the most common sensors on a mobile platform, which is an accelerometer that of course is used for many different types of uses, such as, for example, let's say controlling the orientation of the screen, which is maybe the most basic functions, that is also used for many apps, including video games, including, in some cases, some health applications, and so on. So we'll try to understand what is the basic mechanism, what are the things that a sensor such as an accelerometer has in common with other types of sensors in terms of the mechanism, and also how it is implemented in practical uses. So let's start from the basic of the operation. The so-called accelerometer is a sensor of acceleration. So it's an acceleration sensor. ACCE1L. Acceleration. So it measures the derivative of the velocity of the object, and the object is basically the reference systems to which the sensor is attached, along in the simplest possible case, along one direction, one specific direction. In practice, in the example that I always make of mobile phones, the acceleration sensor measures the acceleration along three orthogonal axes. So the acceleration of the object in a 3D space. Okay. Now, for the purpose of understanding the principle of operation, we're going to focus on an accelerometer along just one direction. Okay? Because the principle, it's easier to understand in that way. But of course, in practice, it is, let's say, multiplied by 3. The other thing that you should have clearly in mind is that, of course, the acceleration is a quantity which is not an electrical quantity. So we need a mechanism to translate this quantity, the acceleration, into something that can be, let's say, treated electrically, also because we need to convert it into, finally, a number, into a digital number. So in the end, the final conversion from an analog quantity to a digital number will be done by a so-called analog to digital converter, for which we need an analog voltage. So we have an acceleration, and we have to convert this acceleration into a voltage. Voltage proportional to the acceleration that we want to measure. Okay? This operation of converting a quantity, the quantity that we want to measure, into an electrical quantity, or in general into another quantity, is called transduction. Okay? Let me just define this one. transduction is the operation of and the object that does this operation is called transducer. In particular, we call electrical transduction is the quantity of arrival is an electrical quantity. So if we are translating certain physical quantity that we want to measure into an electrical quantity, we say it is an electrical transduction. Okay, and the associated transducer will be an electrical transducer. But the concept of transducer is more general, also because in many applications the transduction operation is not direct, in the sense that typically one has to use a transducer to convert the initial quantity, the quantity that we want to measure, into another form, and then to make some additional steps in order to move from the initial physical quantity to a final electrical quantity. In the case of the accelerometer, what we do is the following thing. We start with the acceleration, which is the quantity that we want to measure. And then we convert this acceleration into a displacement. And we need a transducer to do that. Sorry. Displacement is a variation of position. Okay? So the acceleration itself is a second derivative of a position, a second derivative with respect to time of a position. And the first thing we do is translating this quantity into a displacement, which is a variation of position. So basically we are you should notice the following thing. The acceleration is a dynamical quantity in the sense that it's the second derivative with respect to time of a position, whereas the displacement is a static quantity. We measure the displacement at a certain time. Okay? And this is one step. Then actually we need to do another step. We need to transform this displacement into an electrical voltage, into an electrical signal, let's say, in particular, a voltage. This is all analog, okay, in the sense that we have an actual voltage, a real number, okay, associated to the voltage, and then finally we can perform the ID conversion and then of course have a number that we can store in the memory, process in the application, and so on. So in this particular case we need the combination of at least two transducers. Okay? One from acceleration to displacement, and the second one from displacement to electrical signal. Okay, let us focus now on the physical mechanism considering the first transduction from acceleration to displacement. And we consider an example or 1D accelerometer. Okay. Now I really want to stress the basic mechanism. Then, of course, the shape of the components that are involved in this transduction are going to be different in the actual realization of the accelerometer. Actually, we need three components. We need a mass, so a small object with a finite mass. We call it M, a spring with an elastic constant K, and then we need some damping term. Of course, you know that if you put a mass at the end of a spring and you let's say extend the spring at initial condition, what you see, what you observe is the oscillation of the mass, right? Then the damping term is what we call in Italian attrito, and basically it damps the oscillation and it acts like a brake in the sense that it gradually reduces the amplitude of the oscillation until the oscillation stops. So these are the three components that we need, and they are enough to consider the situation. Let me show you a very simplified physical representation. Let us assume that this is the case of the sensor. And the case of the sensor is attached to the object of which we want to sense the acceleration. So it moves together, which means that the acceleration of the object is identical to the acceleration of the case of the sensor case. Okay? Let's assume that we want to measure the acceleration in this direction. So what we want to measure, we want to measure A, the acceleration, which is the second derivative of y. And y is, let's say, the position of the case. A is the second derivative of y with respect to time. Then, in the case, what we have this mass, which is connected to the case through the spring, so the spring with constant K. And then we have this, let's say, damping term, which typically mechanical engineers draw like a sort of piston with some oil so that it really damps the oscillation. You can think of what I have drawn as a simple toy. You have a mass that in principle can oscillate along the y-axis depending on the extension of the spring, and then you have this piston which is damping the oscillation. Okay, this is the basic operation. Let's call this damping term B. Okay, now the position of the mass with respect to the system of reference of the case, let us call it X. Okay. Now, the equation that is governing this motion is the following. Of course, the mass times the acceleration of the mass. The position of the mass is x plus y. So the acceleration is x, the second derivative of x, plus the second derivative of y, is equal to the total force acting on the mass. And the total force acting on the mass is the force of the spring, which is proportional to the elastic constant and to the extension of the spring. So it's k times x, and it's, let's say, moving the mass towards negative y in this direction. Okay, so it's minus here. And then we have a damping term, which is a force going in the opposite direction of velocity. So if x is increasing, so we have a positive velocity, x prime is positive, then this damping term pushes the mass in the opposite direction in the sense that it breaks it. Okay, so it's like minus b x prime. When x prime is positive, you have a force which is pushing back the mass, acting as a brake. Okay, so this is the equation, and this is the quantity that we want to measure. This x is exactly the displacement. Because it is the position of the mass with respect to 0. 0 is the, let's say, x equal to 0 is the, let's say, rest position, because when x is equal to 0, in what I have drawn here, the spring does not apply any force, and therefore we want to translate this a in an x. And you see it is quite easy, because we have written this equation which relates basically a, the acceleration, to the displacement. So we need to operate a bit on this equation, and the simplest thing that we should do here is use the Laplace transform and work in the Laplace domain. So if I work in the Laplace domain, it is relatively easy. This x second derivative becomes s to the power of 2 times x. Okay? So let me continue. In the Laplace domain, we have that m times the second derivative of x become s to the power of 2 times x, minus a plus a is the Laplace transform of the acceleration, is equal to minus kx, the force of the spring, minus bs x. Let's use big X. Okay? So we can collect all the terms that contain X, and we have something like ms to the power of 2 plus bs plus k is equal to minus ma. Okay? So and collect everything, we have minus 1. We can divide everything by m in order to, let's say, have a first order term, a high order term with coefficient 1, and then we have plus b over m times s plus k over m. And you see what we have. We have that the displacement is proportional to the acceleration times a ratio, which is the transfer function of the accelerometer. this is a transfer function with two poles. We have two poles because, as you see, it's a second order denominator. When we have something written in this way, you know, we can basically associate this expression to this one. We can write it like this. But if I consider just the transfer function, we can write it as plus 2 xi omega 0 s plus omega 0 squared, where we have defined omega 0 as the square root of k over m. Just this is of course what comes by equating these two polynomials term by term. So Km is equal to omega 0 squared, so omega 0 has to be equal to k over m, and xi in this expression must be equal to, let's do all the operation, b over m is equal to 2 xi omega 0, which is k over m, which means that xi is equal to b over 2 square root of m k. If you remember something from the, let's say, analysis of the polynomials, this omega 0 is the modulus of the if b is no, let me add something. If b is sufficiently small, the poles are complex conjugate, and omega 0 is the modulus of the poles. So the two poles are like this. They are on a circle of radius omega 0, and xi is equal to, I would say, 1 over, no, is equal to the cosinus of alpha. This is the meaning of xi and omega 0. It's clear. I think it's easy to see that if b is equal to 0, the two poles are pure imaginary numbers of modulus omega 0, so they are plus or minus j omega 0. And if b is not 0 but small, then they are complex conjugate. One is here, and the other one is here. That's it. Here are the two poles. Okay. What is the shape of this transfer function? We can just look at the Bode diagram of the amplitude. So we can plot the x over a, the transfer function in dB, as a function of omega on a logarithmic scale. And of course we have a simple low-pass function, which means that we have two poles, so when omega tends to 0, the transfer function is flat. Then at omega 0, we have a small resonant peak, which depends on xi, and then it goes down with minus 40 dB per decade because we have two poles. Okay? This omega 0, which is the modulus of the poles, is also, from a mechanical point of view, the resonant frequency of the system mass plus spring. Please. Okay. Maybe I can. This is the resonant frequency of the system mass plus spring. From a practical point of view, it means that if you, let's say, extend the spring and leave it free, then the mass is oscillating with the spring at a frequency which is exactly omega 0. Okay. So it has a very intuitive, mechanical meaning. Okay. So why is that interesting? Because you see, if you basically at low frequency, at frequency below omega 0, you see that the displacement x is proportional to the acceleration. You see here, the displacement is exactly proportional to the acceleration. So it is just sufficient that you look at the transfer function of the system at low frequency, which means that you have to take an average of the position of the mass over a sufficiently long time, over a time which is a few multiples of the inverse of the oscillation frequency. Okay. From a practical point of view, it means that if this is the rest position of the mass, which is the position that we have when there is no acceleration, when there is some acceleration, the mass is moving this way. So let's assume that there is an acceleration, then the mass at the end of the spring is moving this way and is oscillating this way at a certain average displacement with respect to the initial position. And this average displacement is exactly x at low frequency and is proportional to the acceleration. Okay? So, as you can understand, it's much easier for us to then translate this displacement into an electrical quantity, because now the displacement is something that is it's let's say a stationary quantity. It's not more dynamical. Okay, so just to show you an example with hand. If this is the rest position, this is the let's say the wall, the internal wall of the case, and this is the position of the mass. This is the situation in which the mass is when the acceleration is 0. Okay. If there is some acceleration, the mass is moving this way. If we increase the acceleration, the mass is moving this way, and so on. No? So that if we measure the average position of the mass, it gives you something which is proportional to the acceleration of the case. Okay? What we measure is the acceleration of the case, and then we assume that the case is attached to the object, and therefore it has the same acceleration of the object. Okay, just to anticipate something that I will, I want to tell you later. Basically, if we want to measure the acceleration along 3 directions, we need to have, as you can imagine, 3 different springs. one that is measuring the acceleration, one that is allowing to translate the acceleration along one direction into a displacement along one direction, and the other two which are doing the same for the other two directions. Okay, this is so basically an accelerometer in 3D is 3 times an accelerometer in 1D in terms of mechanism of operation. It is exactly the same mechanism which is repeated 3 times along 3 different axes. Okay, now just focusing on the principle of operation, we still need to translate this displacement into an electrical signal, and this can be done in many different ways. Actually, there are, let's say, historically and also in the market, different mechanisms that allow this transduction. And the most commonly used, which is the one that we are considering here, is the so-called capacitive accelerometer. That is based on this. Okay. Okay. Is the so-called capacitive accelerometer. There are, as I said, there are many options to go from a displacement to an electrical signal. The capacitive accelerometer essentially transforms the displacement into a capacitance, let's say capacitance. Actually, it is a variation of capacitance, but it's the same thing from a physical point of view. And then we need to transform the capacitance into a voltage. We are passing through this additional step, and we are doing it by using MEMS technology. MEMS is an acronym that stands for micro electromechanical systems, and it's basically, this is the M, it's basically a technology that allows to fabricate mechanical things and electrical things at a microscopic scale on a silicon wafer. So using the same silicon, more or less the same technology that we use for the fabrication of silicon devices. Okay. So why we need the electromechanical systems? Because of course we need some mechanical parts, the mass and the spring. We need some electrical part because we are going to need the capacitance and also some additional electrical components. And this is a single fabrication platform that allows to have all these components on the same silicon, on the same piece of silicon. So, what is the mechanism of operation? It's easy to transform a displacement into a variation of capacitance, because if you remember, if you have a parallel plate capacitance, the capacitance is proportional to the distance between the two, is inversely proportional actually to the distance between the two plates. And then if you have a fixed plate and the moving plate whose position depends on the displacement, then the total capacitance depends on the displacement. Okay? So we need two plates. One is a stationary plate, a fixed plate that is connected to the package, to the case, and then we need the moving plate which is connected to the mass that is oscillating. If d is the distance between the two plates, then the capacitance is proportional to the inverse of the distance. So basically, if I make again the drawing that I made before, basically you need a stationary plate that is here, and the additional moving plate that is somewhat here. Okay? So x in this case is also the distance between the two plates. Of course, this is just a concept of the operation. In practice, things have to be shaped differently. Consider that everything occurs at a microscopic scale. So, for example, the variation of d is something like 10 micrometers. This is the typical variation. So we are measuring, we are transforming the acceleration into a displacement which is just a few micrometers, and this displacement is modifying a capacitance, and then when we have a variation of capacitance, we can translate it into a variation of voltage. So how does it work in practice? Let's try to put all these things together. What we see is that in practice, this plate is the mass, is the same thing. The mass that is moving is the mass of the moving plate. And let me show you a drawing which is not only conceptual, but is more close to the actual realization. Typically, the mass, as I mentioned, is also the plate of the capacitance and is a thin silicon membrane. So a thin layer of silicon, which in cross-section is done like this. And seen from the top, let's assume that, let me draw the case. Let's assume that this is the case. So this is the case. This is the lateral view. Let me show you here a top view. From the top, what we see is the following. Basically, this membrane has a rectangular shape, but in particular, it has some very thin regions, this one, this is the mass, some thin regions, which are this one, which are actually the springs. So these are springs. This narrow silicon line, spring, this is another spring. So instead of having just one spring, we have 4 springs. Okay. This is fixed because the extreme parts of the membrane are attached to the case. Okay, so this is the case. So you see the situation. This membrane basically can oscillate in this direction vertically. The movement is like this. You have a vertical oscillation. Okay, and the possibility of movement is enabled by these very thin springs that we have, because otherwise the membrane would be rigid. Okay, so the important thing of this MEMS technology is that it allows not just to dope in different silicon parts and to pattern the silicon, but also to, let's say, remove the material and have some void regions, have some thin regions and some thicker regions. So this is the additional thing, so that we can really have the shape that we want. We can implement the mass, we can implement the spring. And of course, the damping term is basically enabled by the air in the case, because of course when the spring is oscillating, the air which is present in the case acts as a brake on the membrane. So we have all the terms. We do not need to additionally, let's say, damp the oscillations, because already the air in the case is doing that job. Okay. Now we need the capacitances, and the capacitances are easy because from that point of view, what we need is just to put some fixed plate here on the top. So, for example, this can be a fixed plate, the stationary plate. And the bottom and the top part of the membrane can be the moving plate. So that this is, let us call it D1, the distance between the two plates. So the capacitance is going to be this one. Here we do it by depositing some metal layer on the top part of the silicon. And in practice, what is usually done is not just having one capacitance, but having two capacitances, so that we can make a differential assessment of the displacement. Let me show you why it is useful. If you So this means that we can have another stationary plate on the bottom of the case. And then we can have, for example, the moving plate on the bottom of the membrane, so that we have this other capacitance C2, which is inversely proportional to the distance D1. Now, the point is that we have C that is proportional to 1 over D1, C2 that is proportional to 1 over D2. If there is a displacement, let's assume that we have a displacement delta, which means that the membrane is moving, for example, up by a quantity delta. This is the average displacement of the mass, because this means that the object is accelerating down. So this is relatively easy to understand. If I accelerate down the case, then the mass moves up, oscillating a bit. The average position, the average displacement, let us call it delta, and of course is reducing D1 and is increasing D2. So we have that C1 is proportional to 1 over D1 minus delta, and C2 is proportional to 1 over D2 plus delta, because by the same quantity, D1 is reduced and D2 is increased. Okay, if the geometry is such that the proportionality constant is the same, and the proportionality constant essentially depends on the area and the shape of the plates. But for the moment, this is not of interest to us. But let's assume that the proportionality constant is the same. The interesting thing is to evaluate the difference between the two capacitances, because we have that C1 is equal to, let's say, let's call it this proportionality constant, we can call it D, okay, over D1 minus I need to make an additional assumption. Okay, no, let me remove this assumption. I make it later. Let me remove this assumption. Sorry. So let me write here the proportionality constant as something like K1 over D1 minus delta, okay, and C2 is equal to K2 over D2 plus delta, okay. Then, okay, to first order, in delta, we can make some approximation. Let's consider that the first order is a very good approximation in this case, because as I mentioned before, this delta is very small. This displacement is of about a few microns, and typically the membrane is large, something like a few millimeters. Okay, so we can use this type of approximation. Let me write it this way: K1 over delta 1 times 1 minus delta 1 delta over delta 1. So I can approximate to first order as 1 plus delta over 1. Okay? And again, C2 is equal to K2 over D2, 1 plus minus delta over delta 2, and this is, if I make the first order approximation, this is 1 minus delta over delta over D2. Okay? Now, the difference between the two capacitances, let's call it delta C, is equal to C1 minus C2 by definition, and of course is equal to K1 over D1 minus K2 over D2, you see, plus delta, which multiplies K1 over D1 to the power of 2 minus K2 over D2 to the power of 2. This is a plus. Okay? If we make these two, the first quantity equal to 0, this one, and this is, of course, due to the fact that we can adjust K1 and K2 in the design phase in order to make it equal to 0, then you see that the variation of capacitance is exactly proportional to the displacement. Okay? So, if K1 over D1 is equal to K2 over D2, then the difference between the two capacitances is proportional to the displacement. Okay, so let us summarize what we have up to now. We have first translated an acceleration into a displacement, which is proportional to the acceleration if we do a low pass filtering. Okay, then by using this mechanism, we have translated the displacement into a difference between two capacitances. And now we only need to transform the difference between two capacitances into a voltage. And this is how it works. Okay? We can see, let's say, a simple example of the last transformation. It's okay up to now. Can I move on? Yeah.
C1 and C2 is 1 over D1 minus delta equal K1 over D1 minus delta. Why is equal?
Yeah. So this is let's say this equal. Maybe it's not totally clear. This equal is related to C1, not to this part. So C1 is proportional to this one. Let's assume that the proportionality constant is called K1. Okay, so C1 is equal to K1 over D1 minus delta. We can just remove this part. Okay, K1 is the proportionality constant. Maybe it's more clear. Okay, so C1 is equal to K1 over D1 minus delta. So, now we need to transduce the capacitance into a voltage. And so let's make the final step. The final step is a capacitance voltage. Transducer. And we need some, let's say, electronics to do that. let's assume that we have C1 and C2. So this is the circuit corresponding to the membrane that is moving. And then what we can do is the following, is include these two capacitance into a circuit which is done like that. It's a type of circuit that is called switched capacitor circuit, because as you can see, we only have capacitance and transistors used as switches, such as in the case of let's say digital logic, with the difference that we are now treating analog signals. So what we do is the following: the top node of C1 can be connected to VDD or to ground, by the signal phi1. So these are NMOS transistors, so they can be considered as switches. When the voltage applied to the gate is high, the switch is on. Okay? So when Phi1 is high, the top switch is on, and therefore the top node of C1 is connected to VDD. When Phi1 is down, then the bottom switch is on and the top switch is off. So the node, this node of C1 is connected to ground. Okay? And we do this. This is proportional to 1 minus D1 over minus delta. Let me use this expression that I just used before. And this is equal to K2 over D2 minus delta. Okay? So for the bottom node of C2, we do essentially the same thing for the opposite phases, which means that this is connected to okay, please.
Why is there a minus in C2? Is K...
No, just because everything else. Okay. Now, and then here we need a amplifier operated by a phase phi2 and this by phi3. Okay. Now, this is just an example. I just want you to understand how we can play in order to translate a difference of capacitance into a voltage. So this is an example of, I prefer to write it, switched capacitor circuit. You probably never encountered this type of circuits. You can see there are circuits in which we only have capacitors and switches, in the sense that all the transistors here are used as switches. They are simple. They are simply off or they are on, as in the case of digital logic. If they are on, they can be, let's say, considered short circuit. If they are off, they are open circuits. Okay? And then, of course, we need the amplifiers. These type of circuits are extremely common, especially for sensing applications, recently also for our audio applications. And, but for sensing and measurement applications, they are very, very common. So we just look at one example, which is this one. And they are pretty powerful. So how does it work? What we are doing is exploiting the fact that in a capacitance we have that the voltage is equal to the capacitance over as to the charge over the capacitance. So which means that if we, or CV is equal to Q in general. So if we take a capacitance and we apply a known voltage onto the capacitance, we are putting on the capacitance a charge that is proportional to the capacitance. Okay? If V is known, Q is proportional to C. And V is just the proportionality constant. So this is this means that a variation of capacitance, if we use this mechanism, becomes equal to a variation of charge. Okay, let's consider the operation that it's easier. It's pretty easy to understand. So we have two different phases. During one phase, we have the following thing: phi 1 is equal to 1. Oh, why is that? Phi 1 is equal to 1. And phi 1 negated, of course, is equal to 0. So, just to complete, phi 2 is equal to 1, and phi 3 is equal to 0. This is the first configuration. Okay? So, let's try to understand what this means in terms of these switches. So if phi 1 is equal to 1, look here, it means that, let me draw the circuit again. This is C2 and this is C1. If phi 1 is equal to 1, this bottom transistor is on, so C2 is grounded on this side. And of course, phi 1 negated is 0, so let's say only one of the switches connected to C2 is on, the other one is off, so that we know what is the voltage of this node. And here, you see, from this node, we go directly to VDD because phi 1 is high. So this is connected to VDD. The switches driven by phi 1 negated are off, so we can discard them. So this is the situation. And so this is the amplifier. Then phi 2 is 1, which means that the input is inverting input is connected to the output, and phi 3 is 0. So phi 3 negated is 1, which means that, let's say, the capacitance CF is connected to ground. So, what does it mean here? How do we interpret this circuit? Of course, here the inverted input is connected to the output, which means that the amplifier is operating in the linear regime. And here, what we know is that the voltage on this node is 0. It is at virtual ground. In Italian è cortocircuito virtuale. This node is at 0. Okay? So if this node is at 0, the voltage on the capacitance C2 is 0, because it goes from 0 to 0, and therefore the voltage on the capacitance C1 is equal to VDD. So we have on C1 a charge, let's call it Q1, that is equal to C1 times VDD. Okay? If we consider capacitance CF, also CF is at 0 volt, because of course this node is at 0 and the other node is at ground, so it's also at 0. So we have that C1 is charged to VDD, so it has a charge Q1 equal to C1 times VDD, and the other two capacitances are at 0. Now, second phase, we have a switch of everything. So phi 1 goes to 0, phi 2 goes to 0, and phi 3 goes to 1. Now, of course, things change. What happens is that, let me draw again C1 and C2. And now C2, the bottom node of C2, goes to VDD, because the switch driven by phi 1 negated is on, and the bottom of the top node of C1 is connected to ground. So basically we have switched the, we have inverted the voltages on the top and the bottom of C1 and C2. Okay? This is just what we have done, nothing more than that. Then, considering the rest of the circuit, we have the amplifier. And now we have this operation, because phi 2 is off, is low, so the switch is off, and then CF is connected to this switch which is on, which is connected to the output of the amplifier. So we are in this situation, and this is we are in this situation. Okay, this is the out from the output to ground. Now, what is happening here? It is happening the following thing. Now, this is again at 0 for the virtual ground. So now you see that the voltage on C1 is equal to 0. And the voltage on C2 is equal to VDD. So if I take the voltage from here to here, this is going to be minus VDD. Because this is 0, this is VDD. So what is happening here? The charge on C2, and probably it's even better not to change the, because otherwise we can use this, we can call it VDD. We consider this positive and this negative. Now, we have a charge on C2, which is Q2, that is equal to C2 times VDD. Okay? This is the let's say the easy part. Now we should try to understand exactly what is happening to the charge which was on C1, because you see there was some charge on C1. After this switch, the charge, that there is no more charge on C1, but the charge which was on C1 can go only towards C2 on towards CF. There are no way in order for this charge to go away. Okay, so we need a bit to understand what is happening of the charge that was on C1. Okay, now let's focus on that part. Now, if there is a charge Q1 on this capacitance C1, what we see is that, for example, there is a charge that is plus Q1 on the top, on the positive plate, and it is equal to minus Q1 on the negative plate. So the charge on this node was minus Q1 in total, because on the top plate of C2 there was no charge, because C2 was at 0. So we had initially a charge in Q1 on this node which was equal to minus Q1. Okay. Now, after the switch, when we are in the phase 2, what we have is something different, because you see here the charge is 0 because C1 is depleted, but here we have a charge which is equal to minus Q2. So the charge which was minus Q1 now is a part minus Q2 on the top plate of C2, and the rest has only one way to go, because it cannot enter the input of the operational amplifier, because we have no current for the virtual ground at the input of the operational amplifier. So the difference can only be here on this capacitance. You see, because now if we sum up minus Q2 minus Q1 plus Q2, we obtain as a total minus Q1, which was the initial charge. Okay? So the charge on CF is minus Q1 plus Q2. Which means that, of course, we need to have the opposite charge on the other side, but of course this can easily be provided by the output of the amplifier, which can provide whatever charge you need. Okay? So the voltage on the capacitor, on the CF capacitance is VF is equal to minus Q1 plus Q2 over CF. And V out, since the positive node of CF is at 0 voltage, V out is equal to, just to finish, V out is equal to minus VF, therefore is equal to Q1 minus Q2 over CF. But Q1 and Q2 are C1 VDD and C2 VDD, so we can put VDD out. And we have what we want. you see we have what we want, because now the output voltage is proportional to the difference between the two capacitances. You remember that the difference between the two capacitances was proportional to delta, which was proportional to the acceleration that we want to measure. Just let me show you this video. This is just a one-axis accelerometer. I could not find the one with a multiple axis accelerometer. There was no.
Vehicles and modern consumer electronics are unthinkable without acceleration sensors. The sensors detect vehicle impact as well as the smallest movements of a smartphone or wearables. The acceleration sensor consists of a signal processing chip and a micromechanical comb-like structure.
Let me go back.
The acceleration sensor consists of a signal processing chip and a micromechanical comb-like structure. These combs form a capacitor, and the distance between the microstructures determines its capacity. The blue part of the structure is movable.
So just let me stop. Basically, in practice, it's much more common to have let's say the moving parts, the ones fabricated with MEMS technology, on a different die with respect to the electronics part. Okay, so with respect to what we have, what I've shown you, it means that C1 and C2 and all the mechanical parts are on this chip that is shown here. And the rest, the switches and the amplifier and the analog to digital conversion is on another chip. This is more common now because then the technology can be optimized for the different uses. In principle, one can do everything on the same silicon die, but this is more common because it allows to use, let's say, optimized process for the two different things. Of course, in this way, the packaging is more expensive, but I mean, it really depends on the situation. These are just wires that connects you see essentially you have three nodes. For example, between this one, this is the central node. I would say that. No, this is the central node between the two capacitances, the part which is moving. You see that here this is connected to the part that is moving, the blue one. This is the top plate, and this is the bottom plate, for example. And these are fixed. And the blue one is the moving plate. Okay, then if you go on.
Depending on acceleration or deceleration, they change their position relative to each other. The resulting change in capacitance is detected by the integrated electronics, converted into a measured value, and output into a voltage signal.
That's it. So in this situation, the movement is lateral instead of vertical, as I've shown you before. But in practice, if you want to have a 3D accelerometer, you need to exploit both. You have to exploit the vertical movement in this direction, a lateral movement in this direction, a lateral movement also in the other direction, and also a vertical one. Okay, you're extracting a difference between capacitances for the movements in all the three different directions. Of course, the object is more complicated, but I cannot find it. Actually, 1D accelerometers are used in some applications, especially in airbags. The airbags are the first type of mass market for accelerometers. Because at some point they became compulsory on all vehicles. And of course, they need only to measure acceleration in the direction of motion. in the longitudinal direction of the car. When the acceleration goes above a certain threshold value, of course, the accelerometer gives the signal, and then the airbag explodes. This is how it works. When in the case of a smartphone, you typically have a 3D accelerometer. And you actually, do you remember what I said when I showed you the iPhone situation? In the iPhone and in all high-end smartphones, you have typically two types of accelerometers, two types of 3D accelerometer. One, which is extremely low power, and that is used always, that is always on. That is low power and not very precise, but is basically used for let's say, detecting the orientation of the screen, I mean, the easy things. And also the steps is the same one that is used for the steps. You do not need a very precise accelerometer in order to understand if there has been a step or not. Okay. While on the other hand, if you want a very precise accelerometer to be used, for example, in games, then you turn on the precise accelerometer, which also consumes a lot more power. In all sensors, you have this typical trade-off between power consumption and precision. So, and of course, in cheap phones, you use just one and try to find a trade-off between the two things. In high-end phones, you can use two accelerometers, one very low power in order to, let's say, have a longer battery duration for most of the applications. But when you need a very precise measurement of the acceleration, you just for those few minutes, then you turn on the high consumption accelerometer. Okay, now a connected concept to the accelerometer is the gyroscope concept. And the gyroscope is fabricated with a very similar technology